Welcome to qnawire.
Okay, this is problem number 2 of chapter 23. What we're given to start is the lambda. Lambda value of the green light is going to be equal to 540 nanometers. And we're going to convert this to meters. So 10 to the negative 9 meters is equal to 1 nanometer. So when we simplify this, we get 540 times 10 to the negative 9 meters. And the reason we're converting to meters early on is because all the other calculations are going to be in standard units. Okay, aside from this, we are also given the slit separation. So D is equal to 0.50 millimeters, which again we're going to convert to meters. So 1 millimeter is equal to 10 to the negative 3 meters. Okay, we're dealing with light here, so light is represented with the symbol C, and this is equal to 3.0 times 10 to the negative, well, to the positive 8 meters per second. And we can calculate this as lambda f. So the first part of this question asks what quantities can we determine using this information given? Well, we can solve for the frequency of the light. So frequency is, what we have to do here is we divide both sides by lambda. So this is just going to be equal to C over lambda. Let's go ahead and plug in our values. We already know what C is. C is this. And we know what lambda is, and lambda is already in meters here. So notice when we plug in lambda here, we get meters cancels out with meters, and all we're left with is inverse seconds, which is hertz. So if you plug this into the calculator, you get approximately 5.55 times 10 to the 14 hertz. Okay, so that's the start. That's one of the first one physical quantity that we could determine with the information given. Okay, let's also determine the angles for constructive interference. So here is our double slit experiment. We have the two slits, the separation D, and then we have the screen distance L apart. This angle, so this is the angle formed from the 0th order bright fringe to the 1st order bright fringe, given by the angle theta 1 here. But in general, we can use the formula d sine of theta sub m equal to m lambda, where m is 0, 1, 2, 3. And this is for the bright fringes. Okay, so we can use this equation. Notice that we know d, we know lambda. All that can vary is m, so we can solve for this angle of deflection to a bright fringe by solving this equation here. So let's go ahead and divide both sides by d. So we have sine of theta m is going to be equal to m lambda over d, and then we take the inverse sign on both sides so that we isolate theta. So we take the inverse sign on both sides. Okay, let's calculate the angle to the first bright fringe. So we're calculating theta sub 1. So m is equal to 1. So all we have to do is copy this equation and plug in the values with m is equal to 1. So m is going to be equal to 1 here. Lambda is this quantity up here in meters. And then our d, the slit separation, is given by this quantity here, which is also in meters. And the reason we converted to meters beforehand is so that meters could cancel out with meters here. Try this on your calculator in degree mode, and you should get something that's approximately, let's see, 0.061 degrees. We can repeat this calculation when m is equal to 2. So it's going to be the same calculation, we're just going to change m to 2. So let's go ahead and do that. Here's the same equation. We're going to change m to 2, so it's the same input as before, except the m is going to be changed. Let's go ahead and change that m to 2. There it is. We plug this into the calculator, and you get approximately 0.123 degrees. Okay, so these are three physical quantities that we can immediately determine with the information given. We have the frequency, the angle to the first bright fringe, the angle to the second bright fringe, and notice that we could keep on going to any order that you would like here. But I think we'll stop here at these two for this first part of the question. Notice that this angle is small, so we can use the small angle approximations to answer this second part of the question. The second part asks, what should we do so that we can double the distance from the zero order bright fringe to the first order bright fringe? So this distance y1. So from the geometry in this situation, you can see that tangent of theta 1 is equal to y1 over L, where L is the separation. However, for the first bright fringe, the angle is small, very small, so we can use small angle approximations. So for small angles now, we can approximate tangent of theta 1 is going to be approximately equal to sine of theta 1. From this equation here, right here, from this equation, sine of theta 1 is just going to be lambda over d, right? If we plug in 1 here for m, so we can set this equation equal to sine of theta 1. So let's go ahead and do that. So tangent of theta 1 is y1 over L, and sine of theta 1 is equal to 1 times lambda, which is just lambda, over d. So let's solve for y1 here. y1 is going to be equal to L lambda over d. So for a given wavelength here, what can we do so that we can double y1? Okay, so one thing we can do, so if this is our expression, what would happen if we double the length? So let's calculate that. If we were to double the length, let's call this y1 prime. If we double the length and we use the same formula for the first bright fringe, we're going to get 2L lambda over d. But lambda times L over d, that's exactly equal to our original y1, so we've effectively doubled our distance to the first bright fringe. So one thing we can do to double the distance is we can double the length L. We can double L, and that would cause y1 to get doubled. Looking at this equation here, y1 is equal to L lambda over d, we can also have the slit separation. By having it, we would achieve the same effect. So let's go ahead and verify that. So let's call that y1 prime again. What would happen if we have that slit separation? D over 2. So notice that since we're dividing by this fraction, we're going to multiply it by the reciprocal of this quotient. So it's going to be L lambda times 2 over D. But if we put this 2 in front, we realize that this is just 2 times our original y1, like so. So we can double L, or we can have D. And the result of both actions will be y1 will get doubled. Okay, so that answers part C of that problem.